Greetings. We are here today to investigate some internal forces and moments. And in this problem, we're asked to solve for the internal forces and moments that live at plane CC. So we're going to look for internal normal force, internal shear force, internal bending moment at plane CC. And since this problem's only asking us about a single plane, I'm going to simplify my notation and just refer to them as N, V, and M. Okay, first thing we need to do is create a free body that cuts through plane CC. And to do that, I'm going to copy over my loading diagram here. And what I want to emphasize here is that when you take some little imaginary scissors and you cut through the fibers of a beam to expose the internal forces and moments, you're also cutting through any distributed load functions that happen to be on that beam. So as I get into making my free body, I have to decide whether to take the left or the right piece of this. And I'm going to choose to take the right piece here. So there's my cut plane. We're going to have a reaction over here at B. We haven't calculated that yet. That's B sub Y. And the amount of load I want on this free body is equal to that portion of the loading function. The load is 0.5 kilonewtons per meters. 0.5 kilonewton per meter, and the length of my free body is 0.6 meters. Right? So half of 0.6 is 0.3 kilonewtons is how much force is going to be on this free body diagram. And I'll go ahead and get rid of that one. I don't need that layer anymore. And the only other thing I'll need to put this free body in static equilibrium are my internals. So by inspection, my internal normal force is equal to 0. So I could actually have omitted that arrow from my free body if I wanted to do so. But as long as I state somewhere that it's equal to 0, it's okay to include it. For my positive internal shear force, shear positive up, down, positive internal moment, positive moment on this side of the cut plane is a clockwise moment, so the moment that tends to make that portion of the beam smile. We put those in as our defaults. And we will be able to solve this free body diagram after we determine what B sub y is. So I'm going to go ahead and hide that for a while. I figure out what layer I drew on. Okay, this is an easy fix. Give me just a second. Let's try that one more time. Paste. Sorry, just a little error in my various layers. There we go. Okay, so I've got all that together on one layer, and now we need to solve B sub y. So to do so, I want to take a free body of the entire beam. My resultant force is now the area under all of this. It's going to be smack in the middle here. So it's not going to be at, actually it is going to be at plane CC, isn't it? Okay. So my resultant force is equal to 0.5 kilonewtons per meter over a distance of 1.2 meters. Half of 1.2 is 0.6 kilonewtons right there. And in terms of where that is located, actually, let's come back to that. Let's come back to that. Let's go ahead and put our unknown reactions here. So A sub y and B sub y, I'm just going to assume they're both upwards. The longer that overhang gets, the greater the tendency that B sub y is going to be downward. But based on the ratios I see here, I have a feeling that they're both going to be upward. A sub y we know is upward no matter what. B sub y is the one we're not sure yet. All right, and then thinking ahead, so in order to solve one of these, we're going to be doing a moment summation. And so I want to measure from A to B, and that way I can solve for B sub y pretty quickly. So from A to B, that's 0.8 meters. That'll be my moment arm. And from A to that resultant force, so the total distance is 1.2. So I need to go over 0.6. And so if it's 0.6 from here to here, then this little piece here has to be 0.2. Okay, our free body is complete and ready to go. So let's do our equations of global equilibrium. And really all we need to do, if you remember the free body that we want to use, this one here, right here. Okay, so we don't need to solve for A sub y, just B sub y. So we're going to focus our attention on B sub y. So we do summation of moments about A is equal to 0, counterclockwise positive, equations of equilibrium. First term, my resultant force 0.6, distance 0.2. And since I've just got two terms in the system and they create opposite rotations, I'm not even going to worry about positive and negative signs. I'm just going to collect like rotations on both sides of the equal sign. So 0.6 times 0.2 has to be equal to B sub y times 0.8. And so we can quickly get B sub y is equal to 0.5 kilonewtons. And the positive sign confirms that it's upward. Okay, so we can do that with a moment summation. We could also use the lever law. So we have 3 parallel forces in the system, and this middle force is located at the quarter point, right? So this is 25% of the distance. This is 75% of the distance here. So since it's located at the quarter point, that means the near reaction gets 3/4 of the load. The far reaction is 1/4 of the load. So 0.6 divided by 4 will be a different way to calculate this exact same number. Okay, so 1/4 of 0.6. All right, either way, we've got our reaction at B, and that's all we were using this free body for. So we're done with it. I'll take that one away and bring this one back and put our conclusions here. All right, next up we do our equations of equilibrium. Summation of forces in the y direction equals 0, upward is positive. We have 3 terms, V upward positive, resultant force downward negative, B sub y upward positive. Set that equal to 0. Okay. So on the left side, I have negative 0.15. Move it to the other side, I get positive 0.15 units of kilonewtons. Okay, that's the best way to report this answer, with the positive sign. If you would like to report it using cartoon arrows, you must use 2. And so it would be the up-down type of shear force like that. Next up, summation of the moments about the cut is equal to 0. And we'll do counterclockwise positive. How many terms do we have? 1, 2, 3. First term, oops, sorry about that. Again, make a little real estate for myself here. Okay, so first term is what I'm searching for, the internal moment. That one gets a negative sign per our sign convention for equations of equilibrium. Next term is my resultant force, 0.3. Distance from the cut, let's see. So this is 0.3 meters, and this distance is 0.6. I should have labeled that before I made the context diagram go away, but you can refer back to it if that is needed. All right, so 0.6 and 0.3. That one gets a negative sign, tendency to rotate clockwise about the centroidal axis of the cut plane, that black dot right there. And lastly, our last term, we have 0.15 kilonewtons, moment arm of 0.6. And the sign for that last one is positive, thumbs up. You probably or maybe can do this one in your head, do it in the calculator just for illustration. So minus 0.3 times 0.3 plus 0.15 times 0.6. And I zero out. So those terms are equal and opposite already. So there is no net moment on this free body. What that means is that the internal moment at that cut plane is 0. Now, when you have a 0, you don't have to put units with it, but I'll do that just for fun. So that answer is 0. And that's really interesting. Let me explain why. What that tells me is that if I was building this beam in real life, if I was building this beam in real life, and let's say I didn't have enough material to go the full 1.2 meters. Okay, so I'm building this out of wood or something, and I have some scraps. I don't have anything that long. I'm gonna have to splice it together. Well, the ideal way to build this is to find that point of natural 0 bending moment right there. I don't have to transfer a bending moment. I only have to transfer a shear force. So if I'm building this thing, that is where I want to splice the two things together. That is the one plane that doesn't need to transfer a moment. So there's your fun bonus fact for watching the video. That's more of a topic for future courses. Hope you enjoyed this. Have a great day.